Hello, and welcome to this video on creating a Mixture of Experts Vision Transformer. So what this video will do is take the Vision Transformer that we made in the previous video and convert it into a Mixture of Experts model. And so first I have to explain what Mixture of Experts is, and then from there we can just get right into coding and actually making the Vision Transformer. So what is a Mixture of Experts? So on the top we have a regular transformer model. You have your inputs, they go into your transformer block, and then they just go through a bunch of transformer block layers, and then you have your output. In a Mixture of Experts model, what you have is your inputs and outputs, but instead of a transformer block, you have a bunch of transformer blocks that are being selected by a router and then combined back together by a combiner. And then only a certain number of these transformer blocks are active at any given time, given what the router tells, right? And so they go, they expand, you only activate like 2 of the blocks, or 3, or whatever number. These are hyperparameters you can update, and then they get combined, and you have this go. And so what you're able to do here is now you have a model that can theoretically have the intelligence as if though you had 8 transformer blocks, but it only requires the performance and the computational power of 4. So you effectively double the computational efficiency of your model, in theory. In practice, a lot of Mixture of Experts kind of operates in the middle, where, yes, you have the compute power of 4 transformers blocks, but you probably only have the intelligence of like 6, right? So you don't get to the full level of intelligence, but you're a lot more efficient than if you just didn't have Mixture of Experts, which is why we see a lot of Mixture of Experts model, right? So GPT-4 is rumored to be a 220B by 8 Mixture of Experts. So imagine 8 transformers blocks here, and you each like set of transformers blocks is 220B, right? You have Mixtral 8x7B, which is 8 7B models, and so Mixture of Experts is actually a very used technique, and so we're going to build or combine it with our Vision Transformer that we made last time. So the plan, again, is to update the Vision Transformer from the previous video to make it a Mixture of Experts, and then we're going to do a quick and small training run where, just like last time, to actually see the performance of the Mixture of Experts. Now, let's get to coding. Okay, so now let's get started actually coding the model, right? So let's just jump into it. So first, obviously, I want to add an import. Because we're going to be using the softmax function in our Mixture of Experts block, I'll explain that to you when we get there. I'm just going to be importing the functional part of Pytorch as f, and then we're just going to be using that later. Next, what we also have to do is just update the config, right? Because it's the Mixture of Experts, we need to add stuff like number of experts and whatnot. So we have num experts. That's obviously going to be an integer because you can't have like half an expert, and so I'm going to set the default to be 4. And then also the top k, which is the number of experts actually used at any given time. This is also an int, and I'm just going to set that to 2, right? And so to actually explain these, if we go back to the slideshow, we can see that here we have 4 transformers blocks. That's the number of experts we have, and we're going to have the same across the entire model. And 2 of them are active, that's our top k, right? So if 3 would be active and 1 would be not used, we'd have a top k of 3, etc., etc. Cool. Now let's actually make the Mixture of Experts block, right? So we're going to go below the block, but above the Vision Transformer section. And so what we're going to do now is we're actually going to make the MOE block. So I'm just going to call it MOE block, right? And obviously we set up the standard neural network stuff. We'll feed it in the config, as well as the forward, right? And then obviously X. So first, obviously, I'm going to set up the like default stuff we use, right? So I'm going to add the embed dimension. So again, because we're effectively putting in both. We're gonna go back here. We're putting in both the router and combiner into here, into like a pseudo block that's just slightly bigger. right? So the embed dimension is just config dot embed dimension. The number of experts is again config dot num experts. The top k is again self dot top k. Not self, it's config. And then from there, we actually initialize the router and the combiner. So the router, so self dot router, it's just a linear layer, right? Because we don't need anything complex here, and it's going to be taking in the embed dimension, and it's going to be outputting again the experts to actually effectively to use. So I'm just going to label this as the router, and then again we have our actual experts. And so I'm going to show you how we actually do the combiner when we actually do it, because it's yeah, we don't actually need a combiner like layer. We can just use this. So the experts is, again, we're just going to do a module list, right? Except this time we're actually going to be picking the model instead of iterating through them like we had before. Because before we had all the blocks and we're going to be going through them. Here, this is just a list that we can selectively pick what we're actually using. So we just have a block of config. And then we have the config for underscore in range self dot, and then just the number of experts, right? So we just have all the experts in the config. And then that's all we have to do for the setup. And now we have to do the forward, right? So first, we need to get the actual just the details from the input, so stuff like the batch size and the sequence length, right? So just the regular transformer type stuff. And so that's just, and then we're just going to discard everything else, and that's just the shape of X, right? Because we're feeding it in batches. Then we're actually going to get the output of the router, right? So router logits, so that's the output of the router. That's just self dot router, and we feed it in X. Then we have the actual probability. So this is where we use softmax. We're just finding the probability that we will use any given thing, and so f dot softmax, and the input is obviously router logits, and the dimension we're just going to set to -1, right? Now we're just going to select the top k experts. So this is, we're just effectively randomly sampling here to actually find the experts that we want, and so then top k indices, and that's just going to be Pytorch dot top k function, and so we're going to feed it in the router probabilities as well as self dot top k, right? We're going to be feeding in the top k that we want to pull out as well, and obviously dimension -1. We don't want to touch the dimension. Next, we're going to be updating the probabilities, and we're just going to be taking the top k probabilities, and then we're going to divide it by the top dot. We're just going to sum them up, and we're going to, keep them equals true, right? So all we're doing here is basically normalizing the values so they're actual probabilities, because what Torch the top k does is it just outputs the regular probabilities without actually dividing them by the total number, right? So this is softmax without the division. Next, we're going to calculate the expert outputs, and we're not actually going to be ignoring the experts that we don't we're not going to be actually avoiding calculating the experts that we don't use here, but that's an optimization you can make later. So torch.stack, and then we're just going to do expert x for expert in self.experts, and then again we're going to set the dimension, so the dimension equals 2, and then we're going to actually filter out the experts that we actually care about, right? So top k indices equals Obviously, we're going to have to modify the top k indices to actually get the ones we want. Unsqueeze. That's one. Dot expand. And remember, -1 just says we're not changing the dimension here, right? So we're effectively keeping it the same. Embed dimension. And then now we're actually going to be selecting outputs, right? So selected outputs, and that's torch.gather, right? But we're only gathering dimension of 2, the top k indices, right? So we're only gathering that many. And so then the combined output of them both, I'm just gonna like multiply them together, right? So selected outputs. So again, selected outputs, we're adding these in, but then we're also just multiplying it by the top k probabilities. So the probability is just kind of like a weighting in this instance. So we're going to be computing all 4, but we're going to be weighting it by a certain amount, right? And so then squeeze. That's one. And then we're obviously going to be summing them up with the dimension of 2, right? So basically, how we're implementing mixture of experts in this thing is instead of ignoring the 2 of the blocks, we're just going to be weighting them differently. And so if you want to optimize the compute later to actually ignore 2 of the blocks, you can do that by just like, doing a legitimate full ignore. And so then you have the combined output, and so we're just going to return that. And now to edit it here, instead of just regular blocks, we're going to set this to MOE blocks. And so there you go. Now we're going to obviously have to edit our training file because we've made it more computationally intensive. But because we've made it more computationally intensive, we should need less epochs to actually train. And so because we again have 4 times the computational usage, I'm going to lower the compute usage here by roughly 4x. So I'll set it to like 15. Right? So it's a little bit more than 4x, but this should still take the same amount of time to train. And so then what we're going to do now is start the training run, right? And so it's going to go, and it's just going to start the training run. And so as you can see, each step here is going to take like roughly 3 minutes. And so 15 steps is 45 minutes, which is similar to what we had last time. So I will see you guys when the training run is complete. So the training has now completed. And so as you can see, we achieved a very similar accuracy to our base vision transformer on a lot less epochs, right? And so what this means is we're able to reach similar accuracies with mixture of experts with a lot less data than we need with regular vision transformer, like a regular transformer model. And so even though this did take more compute during training, in the end, because you're able to use less data, now you're able to effectively use higher quality data to get this to the same level and thus improve the model. And so this is just one of the many techniques you can use to help improve your models. And so from here, you can go on and you can say, make this more computationally efficient. Maybe do something sort of similar to Snowflake's Arctic model. We have a ton of experts, right? Because that model had 128 experts, but only used a very small number of them, right? And so then you can get massive compute savings that you can't just do with a regular transformer. And I'll leave it at that. I hope you guys enjoyed this video. Like and subscribe if you want more content from me. Thanks for watching.